Hey students, Mr. Murphy here. Lesson 4, numbers raised to the 0th power, right? So remember here, we know that a number raised to the 0th power is equal to 1. So that's what we're learning today. We recognize the need for the definition to preserve properties of exponents. The reason a number raised to the 0th power is 1 is because if it isn't, then our rules that we have been using for the last couple of lessons won't work. So let's review what we know. If we're multiplying exponents with the same base, then you just add the powers. So x to the mth times x to the nth equals x to the m plus n. If we are raising a power to a power, so x to the m raised to the nth power is x to the m times n. So we multiply the powers. If we have powers being raised, so if we're multiplying two numbers and they're being raised to a power, then each number is raised to that power. Okay. Division 1 was if we have the same exponents and they're being divided, we subtract the powers. So basically 1 and 2 are the same, 3 and 4 are basically the same but slightly different. They're related because these are being multiplied and these are multiplying or dividing exponents. Okay, so let's extend what we know to division. So assume x does not equal 0 because you can't divide by 0. So x to the mth power divided by x to the nth power equals x to the m minus n. So that's our division rule. Now we're going to assume that y is not 0. So x to the x over y to the nth power equals x to the n divided by y to the nth. So those are the rules we've had. This is just kind of a refresher of that. So division is the inverse of multiplication. So the rule for multiplying exponents is to add powers. Then the rule for dividing exponents means subtract powers. Okay, and we've proved this in the earlier lessons. X to the 7th divided by x to the 4th means x times x times x times x times x times x divided by x times x times x times x is these 4 x's cancel out, become 1. So I have 3 left over. So 1 times 1 times 1 times x times x times x equals x to the 3rd. Basically, 7 minus 4 is 3. So our answer is x to the power of 3. The product rule, if I have a fraction raised to a power, or if I'm dividing or multiplying raised to a power, or dividing raised to a power, then each individual term inside there gets raised to the power. So if we look at this, 5 over 7 to the 5th power is 5 over 7 times 5 over 7 times 5 over 7 times 5 over 7 times 5 over 7. So I can rewrite 5 times 5 times 5 times 5 is 5 to the 5th. And 7 times 7 times 7 times 7 is 7 to the 5th. Okay, so numbers in exponential form raised to a power. Go back, go over here. Raised to a power. Does x plus y raised to n equal x to the nth plus y to the nth? So let's try it with real numbers. 3 plus 4 to the 5th would be 3 plus 4 times 3 plus 4 times 3 plus 4 times 3 plus 4 times 3 plus 4, which is 7 times 7 times 7 times 7, or 7 to the 5th. Is 3 to the 5th plus 4 to the 5th equal 7 to the 5th? Well, no, because I cannot add these because they're separate. They're different bases. And if I multiply them out, 3 to the 5th is 243, 4 to the 5th is 1,024. If I add them together, I get 1,267. Whereas 7 to the 5th is 16,807. So they're not the same. We proved that they're not the same. And the reason they're not the same is these bases 3 and 4 are different. The rules of exponents only apply if the bases are the same. So if I'm multiplying, and when I'm multiplying and dividing, okay, bases have to be the same, and I'm multiplying, dividing, adding, and subtracting. It doesn't work. So the numbers in exponential form x minus y to the nth, is that going to be x to the nth minus y to the nth? No, because we're subtracting. It only works in addition, in multiplication and division, not in adding and subtracting. So x to y, x times y to the nth is x to the nth times y to the nth, because we're being multiplied. X divided by y to the nth equals x to the nth divided by y to the nth, because we're dividing. X plus y to the nth does not equal x to the nth, y to the nth. And x minus y to the nth does not equal x to the nth minus y to the nth. Okay. What does all this have to do with 0? Well, let's take a look. What happens if we have a fraction x to the 5th divided by y to the 5th? If we use our rule, we expand it out, x times x times x times x times x divided by x times x times x times x. All of these separate into x divided by x, and they're all 1. So 1 times 1 times 1 times 1 times 1 is still 1. If we use our rule for subtracting exponents, if we're dividing exponents with the same base, then we subtract the powers. So x to the 5th divided by x to the 5th is x to the 5th minus 5th, which equals x to the 0. And we just proved up here, x to the 5th divided by x to the 5th equals 1. So x to the 0 has to equal 1. So try this with any number. So try it with 7 to the 5th over 7 to the 5th. Try it with 85 to the 92nd over 85 to the 92nd. Well, obviously, it's basically the same number on top and bottom, right? And our rule for fractions is if we divide by the same number, we get 1. That's the rule for division. Anytime you divide a whole number divided by a whole number, the same whole number, you get 1, or a fraction, or a decimal, or any real number. So for all real numbers, as long as the number is not 0 and you're not dividing by 0, that number to a power divided by that number to the same power equals 1. Okay. So what if the power is 1? We should know this, right? If we have x to the 7th divided by x to the 5th, 6th, then x to the 7th minus x to the 6th equals x to the 1, which is just x. Okay. X to the 1, any number to the first power is that number. Any number to the 0th power is 1. All right, let's take a look at this one. Jacob says 2 to the 5th times 4 to the 3rd equals 2 to the 11th, because 4 to the 3rd is 4 times 4 times 4, and 4 to the 3rd is 4 times 4 times 4. And each 4 is 2 times 2. So we got 2 times 2 times 2 times 2 times 2 times 2. Is it correct? So 2 to the 5th plus, or times 2 to the 1, 2, 3, 4, 5, 6, 2 to the 6th. Is that right? Your answer. Okay, homework and online Khan Academy for extra help and student workbook, page 16. Good luck.